In this session on quantum chemistry, we're going to be exploring the phenomenon of quantization and the wave function. So just to quickly recap on the origin of quantum chemistry, the first observations of quantization came from the hydrogen line spectra. So the fact that we see these dark lines in the absorption spectra, or we see an emission spectrum from hydrogen at specific wavelengths, tell us that there is quantization of energies going on. So the lines interrelate, and Johann Balmer found a pattern in these lines, but this particular pattern only worked for the Balmer series, a series that carries his name. So you'll already be familiar with the fact there are a number of different emission series from hydrogen. The first three are shown here, but Balmer's prediction only worked for one of them. So it was transitions from the initial orbital to the final orbital of 2. So this middle series here was the Balmer series, but it didn't explain the other two series that were visible in the visible spectrum. So the first thing I'd like to say is just check that you're happy that this is the same as the previous statement of the Balmer series from semester 1. The problem was this didn't give a solution for all the series, so the Paschen series and the Lyman series weren't accounted for by this observation. It took the intervention of Johannes Rydberg to find a general solution for all of this, where the frequency of emission could be found using this particular formula here, with a constant which carries his name. So the Rydberg constant, just a quick beware, it carries a number of different units. Here we've used hertz, but it could also be in wave numbers. There are many different ways of expressing it. The only way we can explain these line spectra observations is the fact that the energy levels are quantized. Niels Bohr came up with the idea that electrons exist in orbits around the nucleus and can only exist on those orbits, so each orbit had a fixed energy. His equation for this looks rather complicated at first, but notice that we've got a pi, we've got the mass of the electron, the charge in the electron, and Planck's constant, so all of these boil down to a constant, and there's a simpler way to look at it and just represent it as the energy is proportional to 1 over n squared, where n is a quantum number, so an integer, 1, 2, 3, and so on. The Bohr atom, as he said, exists in orbits, where the electron resides on one of these orbits. These orbits are fixed, and the energy of each one is defined, and consequently this led to the idea of quantization in the atom, and resulted in Bohr being awarded the Nobel Prize for his investigation of the structure of atoms and the radiation emanating from them. But the problem was it only worked for these hydrogenic atoms, so atoms with a single electron. So helium plus, lithium 2 plus, and so on and so forth. The minute a second electron was put in there, things got a little bit confusing. In order to understand more about this, we need to consider the electron itself. And that brings us on to the topic of quantum chemistry. So in this course, we're going to look at a number of things. We're going to look at the wave description of matter, specifically how it relates to the chemistry that we're looking at. We need to look at the properties of the waves and the mathematical connections, because it's the mathematical connections that allow us to understand what's going on. We then need to introduce and interpret the wave function, what this particular thing means. And using this, we're going to build theoretical models to help us understand what's going on in the chemistry that we observe. We're going to be looking at particles in boxes, so in a 1D box or a 2-dimensional box. We'll be moving from the 2-dimensional box into a particle on a ring, so thinking about rotational motion. We'll be thinking then about particles on spheres, so starting to think about electronic energy levels. Once again, a quick recap on waves and particles. So Louis de Broglie had his relationship which related the wavelength observed with a momentum. So this meant that if light as a classical wave can show particle behavior as evidenced by Einstein's photoelectric effect explanation, can the electron, which is ostensibly a classical particle, can it show wave behavior? And as a result of the studies, Louis de Broglie was awarded the Nobel Prize for his discovery of the wave nature of electrons. Sure enough, studies later done showed that the same diffraction pattern appeared for electrons as happened with diffracted X-rays. So electrons do indeed have wave behavior. The problem is describing particles as waves is not a trivial problem. Light and matter are intrinsically related, but this wave-particle duality that you've come across, this idea of considering something simultaneously as a particle, as a wave, it's only a tool to explain behavior, and it doesn't fully explain the observations that we want to see. Consequently, we come up with something called the wave function. A wave function is quite a tricky thing to picture. However, if we simply view it as a mathematical function which describes the wave behavior of particles, it is quite literally just a description. We view it as a guiding wave. It's what guides a particle through space, and it contains information about every aspect of the system. It carries this symbol psi, the Greek letter psi. There's a great article in Physics World published a few years ago explaining different ways of looking at psi and ways of picturing it and what the wave function actually means. In the quantum mechanics that we're looking at, psi appears, the wave function appears in the Schrödinger equation. This is one form of the Schrödinger equation. There are many different forms, but if we just break it down quickly, it is something called a differential equation. What this is saying is that the outcome of the equation here on the right-hand side depends on the rate of change of the function itself. So if we break this down, we have a function of x, which would be the value of the function, so that's this psi here. We have our f prime of x, which is how quickly that function changes, and the f double prime, the second derivative, which we're showing here in red, tells us how curvy the function is. So for this particular iteration of the Schrödinger equation, we're looking at how curvy the wave function is. This particular variant of the Schrödinger equation will determine the energy of the system, and it links the kinetic energy, shown by the derivative here, and the potential energy of the system. So the two types of energy that we're mainly considering. It's often shown in a much simpler form down here. It's important to recognize that we can't simply cancel the psi here, because this h, this hat here, represents a Hamiltonian operator. An operator is simply an instruction which tells us what to do on the wave function. So if we had square it and add 2, that is an instruction. So we could say our Hamiltonian is square it and add 2, and that would give us a value at the end. Interpreting the wave function is important as well. As we said, it's a guiding wave for matter. So if we think of a particle moving through space, the wave function is intimately attached to it and explains the way in which it moves through space. It fundamentally describes all the observables in a system. So from the wave function, we can determine the momentum by using the momentum operator here, p hat. We can determine the energy, as we said in the previous slide, by using the Hamiltonian operator. Or we can determine the probability of a position. So if we have particles in space, using the wave function, we can make predictions about where we're most likely to find it. Because the wave function is fundamentally a wave, it can have negative values. If you imagine a sine or a cosine function, it can have negative values. So because psi can be negative, and we can't have a negative probability, the probability has to be positive. Consequently, we must have a psi squared term in our probability. The final thing with probability is the particle has to exist, which means we have to be able to find it somewhere. So if we add up all our individual probabilities of finding the particle in space, they should all add up to 1 because the particle exists somewhere. There are a number of rules we need to consider when looking at the wave function, and one of them is looking at the properties of it. There are 4 main conditions that we want to look at with a wave function. And the best way to picture this is to draw pictures, to draw a sketch of an example wave function. So here's one example wave function, but it breaks a number of the rules. The first rule that we want to look at is the continuous values of the wave function. So a wave function has to be continuous. A particle has to be able to move freely from one point in space to another, so its wave function must be continuous. That means here, where we have a break in the wave function, we can't have that. That's not allowed. Another thing is that the wave function has to be single valued. So at any point in space, we can't have more than one probability for finding it. If our wave function has more than one value, that means we have more than one probability. Consequently, we can't have that wave function doubling back on itself, because here we would have 3 values for a probability, and that's not possible at a given point in space. The next condition is that the wave function must be finite over finite space. So at no point can the wave function go off to infinity, because if the wave function goes off to infinity, that means its energy can go off to infinity, and that's something that's not possible. So it can't become infinite. And finally, the last one that we need to look at is it has to have a continuous slope. The last one is slightly harder to picture, but we have to have a continuous slope. Remember that we are going to be doing a derivative. If we take a derivative and the slope is discontinuous, that means the slope is going off to infinity, or it has a break. That means we have a break in the energy values. So we can't have a situation where our slope is discontinuous. The next condition we need to look at is boundary conditions. So what happens at the edges of a system? A particle cannot exist at infinite potential. If we take it off to infinite potential, that means it's got infinite energy, which means it's not possible, so the wave function has to go to 0. Secondly, if we remove a particle to infinity, that means its energy drops to 0, which means the wave function must drop to 0 as well. Fundamentally, this leads to quantization of energies. This is a natural result of all of these conditions, which I think we can all agree are fairly logical. We can't have infinite energy, and we can't have infinite separation. The next thing to consider is what form the wave function has. What does it look like in terms of the mathematics? So for a free particle moving in one dimension, there are a number of things we can have. But one of the forms of the wave function is this one here, where we have the complex form of the exponential, which by de Moivre's theorem expands to a cosine and a sine function. I'll refer you back to the maths class from last semester, where you can look at complex numbers. And complex numbers do genuinely make the maths easier, really. So let's plot these functions. If we look at them, let's think about what k and a are doing. So we've just got the real function in blue, the cosine function in blue, and the sine function in red. Well, if we think about a, all a is doing is stretching the wave functions vertically. It is simply a scalar value. K, on the other hand, will change the wavelength of the wave. So it's related to that wavelength. If we increase k, we'll squash these wave functions. If we decrease k, we'll stretch them out. K has a term called the wave vector, which will allow you to easily look this up in books and literature. Uncertainty is another key part of quantum mechanics. So remember, de Broglie connected wavelength and momentum via his equations there. So for a definite wavelength, you would have a definite momentum, and it would continue infinitely. So that wave carries on going to infinity. The problem is, there's absolutely no position information here. Consequently, if we know the wavelength, if we know the momentum, we don't really know a lot about the position. But if we know the position exactly, the more we define the position, the less we can define a wave in that space, so the wave doesn't spread out. So there's no known wavelength, which means the momentum is unknown. Werner Heisenberg defined this in much more detail and called this the uncertainty principle. It relates the uncertainty in momentum, delta p, to the uncertainty in position, delta x, and it has a finite limit of h bar over 2. H bar we will be seeing everywhere. It's simply equal to h over 2 pi. It's called the reduced Planck constant. Fundamentally, we can't know the position or the momentum with arbitrary precision. We always have a limit on how precisely we can measure this. If we look at the effect of classical versus quantum mechanics, uncertainty really isn't applicable in classical mechanics because the uncertainties are so unmeasurably tiny. If we think of a car traveling at speed, with a particular speed of delta v is 1 micron per second, not very fast, we can calculate delta x. I'll leave this as an exercise for you to do it, but you'll find it's not a very big number. Whereas if we go for the electron in a hydrogen atom, if we let the uncertainty be the diameter of the hydrogen atom, and the mass of the electron is this, we can determine the uncertainty of the velocity, and you'll find that because of the scales involved, this is a very, very big number. So at the quantum level, uncertainty becomes a serious issue. To summarize, energy is fundamentally quantized. This is visible in the spectroscopy of atoms, but it's also visible in the spectroscopy that you do in the laboratory, whether infrared or UV or NMR. Fundamentally, if we didn't have quantization of energy, our spectroscopic techniques wouldn't work. We see this evidence all over the place. So because of this, we need to consider the quantum effects. When we get down to quantum levels, wave behavior of matter becomes important. So matter is guided by this wave behavior. And we call this the wave function. It is simply a mathematical description of how matter behaves. There are four main properties that that wave has to have. It has to have continuity, it has to be single valued, it has to be finite, and there has to be a continuous slope. And fundamentally, it's all subject to the uncertainty principle, which simply states that we can't measure the position and the momentum with arbitrary precision.